Hello, my name is Hasan Zerze. Welcome to the fourth video of my calculus lecture series. In this video, I would like to talk about limits and inequalities. I'm gonna give three very important theorems which are very useful in solving the problems and also understanding the limits. The first theorem I would like to give is if limit hx as x goes to a exists and hx is non-negative for all x, then the limit as x goes to a hx is also non-negative. This looks intuitively true, but we need to give the proof to better understand it. And once you prove this, this is a very useful theorem that one can use repeatedly in many examples. So let's say that the limit of hx as x goes to a is equal to c, let's say. And let us assume c is let us assume that c is negative. So basically we are using a method called reductio ad absurdum. Reductio ad absurdum, which means that in order to prove that c is actually non-negative, we are assuming the reverse. We are assuming that c is negative with the hope that we are going to have a contradiction at the end, which will tell us that this cannot be true, and then we are going to prove that c needs to be larger than or equal to 0. So let's assume this for the time being. And if you remember the delta epsilon definition of limits, we can choose, or any number or any value of epsilon can be given to us, and let's assume that epsilon is given as minus c. So this can be given because this is a positive value. If c is less than 0, then minus c is going to be larger than 0. And let's assume that the given epsilon value is minus c. Now we can write that since epsilon is larger than 0, we can write that epsilon is epsilon plus 0. And then we know that hx is larger than or equal to 0 from the theorem assumption. So then this means that this is going to be less than or equal to epsilon plus hx. We have written hx instead of 0 because hx is larger than or equal to 0. Then going forward, since epsilon is given as minus c, this is going to be minus c plus hx. And since this is a positive value, because of this, the value of this is going to be equal to the value of the absolute value of the same thing, hx minus c. So since this is positive, we can take this out of the absolute value. So this should be true. And then we see that apparently epsilon is less than or equal to hx minus c for all x. So we have, because we have not assumed anything other than this one. So this is true for all x if c were negative. But we know that from the limit definition, by properly choosing the value of delta, we can obtain hx minus c is less than epsilon for any given epsilon, for all the values of x which are close to a within plus minus delta value. But this contradicts with this one because it's the reverse of this, which means that this is a contradiction. Contradicts with the fact that this has a limit. And this means that c cannot be negative. And hence, c is larger than or equal to 0. And c was the limit of hx as x goes to a, which means that limit x goes to a, hx is going to be larger than or equal to 0. And this proves that theorem. Now, a second very useful theorem, which is very similar to this one. Let f and g be given two functions. Which have limits for x goes to a. Now the statement comes, if fx is less than or equal to gx holds for all x, then limit x goes to a fx is less than or equal to limit of gx as x goes to a. So this is very similar to this one, other than we have 0 here instead of we have another function here. So, but in order to prove this theorem, we are gonna use the fact that we have proven in this theorem. So proof, since we have already proven this theorem, we can use this conveniently. Let's say fx is less than or equal to gx for all x. Okay, and then this means that if I take this fx to the right hand side, what we're gonna have is 0 is gonna be less than or equal to gx minus fx. And let's call this function as hx. So we're going to have a function whose value is larger than or equal to 0, and this reminds us the previous theorem, right? For all x. Now, we know that since this is non-negative, the limit of hx is also going to be non-negative. So 0 is going to be less than or equal to limit x goes to a hx. And we know that limit of this function is going to be the limit of this function because they are equal to each other. And the limit of the subtraction is subtraction of the limits. So we can write limit x goes to a gx minus limit x goes to a fx. And so this value is larger than or equal to 0, then we can take this value to the left hand side, which is gonna give us limit x goes to a fx is less than or equal to limit x goes to a gx, and that's what we want to be proved. So this completes the proof. Now it's time to talk about a very important and very useful theorem, which is called the Sandwich Theorem. This is a very powerful theorem to find the limits of many different functions. So let f, g, and h be functions that satisfy fx is less than or equal to gx, and that's less than or equal to hx for all x. Now the statement comes: if limit x goes to a fx, if this limit exists, and that limit is equal to limit x goes to a hx, and say it's equal to some value L, then if we know the limit of this and we know the limit of this, and they are both equal to each other, then we can say that limit of gx as x goes to a is equal to the same thing, L, which this theorem actually looks very intuitive, but it's very powerful. Example. So I'm gonna show an example how to use this theorem usefully to find limits of different functions. So my example is gonna be limit x goes to 0 x squared sine 1 over x. So in order to find the limit of something using the sandwich theorem, we need to write some inequalities. So one thing that we know about this function is this part, the sine part, is gonna be between -1 and +1 no matter what the value of x is. So we can write that -1 is less than or equal to sine 1 over x, and that's gonna be less than or equal to +1. So this is gonna be within this interval. So once we have such an inequality, then it's gonna be very useful to use the sandwich theorem. So now the next step is to make this look like this one. How we can do this? We can multiply these three terms by x squared so that we can have this term. And this means minus x squared less than or equal to x squared sine 1 over x less than or equal to x squared, because x squared is always a non-negative value, so I can easily multiply each term by x squared without changing the direction of the less than or equal to sign. then we know that limit x goes to 0 minus x squared. So we know the limit of the left hand side, and that's equal to 0. And we also know the limit of the right hand side, as x goes to 0, and that's also equal to 0. So both the left hand side and right hand side go to the same value 0, and from the sandwich theorem we can conclude that this function goes to 0 as well as x goes to 0. So thus limit x goes to 0, x squared sine 1 over x is equal to 0. So